Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So today we're going to talk about again supercapacitor but in terms of electrochemical impedance spectroscopy EIS in 3 electrode system. So I would like to cover a very short video about the EIS to help you um, discuss your analysis in your journal, either in your thesis. Okay, let's move to the next slide. So the highlight for this video is to talk about the component needed in the EIS and what is the response that we're going to get from the EIS analysis, and also a little bit tips and also tricks to help improve your analyzation data for the EIS. Okay, see from this slide, we have electrochemical impedance spectroscopy. Okay, this is the normal 3 electrode system, whereby for the electrochemical impedance spectroscopy, you can use 3 electrode system to run your experiment. You just need your potentiostat. So here you have the reference electrode. Normally is argentum chloride AgAgCl. And then you can also use a saturated caramel electrode or HgHgCl mercury electrode. So various things you can use for reference. And our working electrode, the same you use for cyclic voltammetry and GCD analysis, you can use the same material with the same substrate for analyzation of EIS. The only thing is you cannot recycle your sample after you run for GCD and CV because it's already charging and discharging. So you need to either run EIS analysis first, followed by CV or GCD, or you need to have separate electrode. Okay, then the counter electrode, you can use platinum wire either for straight line or coil. Coil is better because higher surface area. Okay, then the electrolyte should be the same throughout the study. If you use a 1 molar KOH, calcium or potassium hydroxide, throughout the study, you need to use the same electrolyte. Okay, that's how the component you need before you run the EIS. Okay, so from the right hand side is what you can get from your material. Depend on your application, the graph might be slightly different because this is normal supercapacitor. You can observe here a semicircle and a Waback line. If you study, for example, based on my experience, when you study like solar cell, dye-sensitized solar cell, you didn't see the Waback line here. You only have 2 or 3 semicircle or sometimes 1 semicircle. So it depends on the application of your material. But sometimes supercapacitor also have 2 semicircle. For battery, we have 2 semicircle. For SEI layer and RCT. So depends on your application, the number of semicircle and also the Waback line might be different. But overall, the graph looks like this. This is one of the paper that has been recently published on the bimetallic phosphate with what we call that MXene vanadium carbide. So let's see the axis first, because a lot of analysis you need to understand about the what is x-axis and what is the y-axis. So x-axis you can see is z prime. Okay, this is what we call that the real axis. The value fall from the x-axis here, the z prime, we call that z prime real axis, belong to the capacitance value. So the x-axis belongs to the capacitance value of your material. So later we will see each response, what response can we read from the Nyquist plot. We call that graph, this graph is Nyquist plot. So x-axis belong to the resistance of your material. And y-axis minus z is the imaginary part, whereby it indicates the capacitance of your material. So this is the capacitance of your material, y-axis, and the x-axis is your resistance of your material. Okay, Let's look at the component. What component we need to have, not the component, the response that we need to digest from this overall Nyquist plot. Okay, first of all, you need to fit your graph. You can either use the NOVA. From NOVA, you have a fit and simulation. You can get a equivalent circuit like this one, whereby you can get your RS, series resistant, or some call it solution resistant, and we can get the RCT, charge transfer resistant, and also CPE, constant phase element. Sometimes they are reported as CDL or capacitance value, and also you should have Wabak if you have a straight line here, and also tangent line if your Wabak is close to the 90-degree. Okay, that's the important circuit that you need to have. If your circuit is very fitted, it's a good circuit, means that when you fit, all the lines fall with your fitted simulation. Your chi-square value, you can get the value, we call that chi-square value from the instrument, should be very low. If chi-square value is very low, like 0.01 and below, means that your fitted is very good. Okay, I'm talking about when you are fitted using NOVA, we have the software from the NOVA version. If you don't have a NOVA, don't worry. You can fit your graph using ZSIM, what we call that, using ZSIMs. I think ZSIM Win. We got a software online, free version. The name is ZSIM Win. You can download online that software. So from that, you just need the value of the x-axis, the real. Then you need to have the value of imaginary y-axis, and also the value of frequency, if I'm not mistaken. So from this value, you can calculate or get the circuit from the ZSIMWin software. Okay, that's how to get the value. Okay, let's say you already have the software, you get the value. Okay, see, the first value is RS. So based on the definition, what is RS? So you can read from the paper. So RS, the equivalent series resistance, the intercept on the real axis. You can see the intercept on the real axis. So that is RS. So you can say that it's a series resistance, contact resistance. It's a total resistance actually, meanings definition by the RS. So next we got the RCT, charge transfer resistance. You can see for the charge transfer resistance, you can see a semicircle. This is a semicircle. A circle is like a ball. So this is a semicircle, half of the circle. So the semicircle, we, from the software, they will calculate the diameter of the circle. The diameter of the circle indicates that your charge transfer resistance between your material and electrolyte interface. And then we got the CPE, constant phase element, indicates the inhomogeneity of the electrode. When you have modified your electrode, so you got the reading on the CPE value. Then Wabak line, when you have a line, this line we call that the Wabak line. The shorter the Wabak line, the better, because faster ion diffusion. And a tangent line. Tangent line, if your Wabak line is less than 45 degree, means that it's close to the y-axis, then you need to add a tangent line to fit your circuit. So overall, what I can say that overall, this is overall, what I can say that we need to have the resistance value as low as possible. So the RS series resistance, the charge transfer resistance need to be the low the possible to indicate or enhance the ion transport and prove the enhancement of your specific capacitance or specific capacity. It's the same when you jump to different application. When we jump to the Dyson solar cell application, we also want to have a low resistance. The same goes for others, because low resistance indicates high. electron conductivity of the material. So that's the response that we need to have from our Nyquist plot. So what is the tips and trick to do so? Okay, like EIS, mostly your tips and tricks fall behind your management or fall behind your skill during you run the experiment. Okay, some you can get very smooth graph like this, then you when you fit from the software is well fitted. But rarely you can get a very smooth graph. Okay, first avoid distraction. Make sure you run your experiment in Faraday cage to avoid any distraction or any noise, because any noise, a little noise, will make a disruption on the Nyquist plot. Okay, number two, okay, make sure you use a fresh sample. Don't use the sample after you run the what we call that GCD, the stability, then the value might be different. If it's needed for your analysis, you want to compare before and after stability, is good. But if not, if you want to run your impedance only, just need a fresh sample. Okay, that is important. Okay, then so far I think that's all. Nothing much different to get the EIS. Depend on your machine. Some machine need the open circuit potential. Some doesn't need the open circuit potential. When you study sensor, it's very crucial to know the OCP. But supercap, I think not very crucial. Even the solar cell is not very crucial. Okay, then determine your amplitude. Amplitude is very important. You need to key in. I forgot to tell you what value to key in. You need to key in the amplitude. Normally we use is 10 millivolt. Then amplitude is how high, the height of your wave. Then we need to key in the frequency range. If you study, you want to see the what we call that here, the 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 Waback line interaction, you need to use a very low frequency, for example, from 1 megahertz to 0.01 hertz. If your Waback line is not so important, like in solar there is no Waback line, just go until 1 hertz or 0.1 hertz. So the frequency range also play around. Okay, next, I think that's all. After you know your frequency range, you include your frequency, then point per decades, you can actually get your analysis done. So most of the time, the only difficulty for them is how to fit the graph. So that's a little bit tips and trick when you are fitting the graph. Maybe in the next video, we will see how to fit the EIS graph. But I think I already published one of that. Okay, I think that's all. I hope it's not much, but a little bit it can help you in your research. Okay, that's all. Bye. See you again.